So welcome student, welcome to the new session. In this session I'm teaching you this first half of this topology course, okay, and this is course number MA425 topology. Okay, so 1 minute. Then yeah. Okay, so now let us start our first lecture. So this is, you can say that lecture number one. Okay, so before we going to start the formal definition, so let me just give you some idea. So what do you mean by topology? So far you have learned analysis, where you have learned kind of open sets, closed sets, okay, and like many other analytical property, right? Like continuity, defensibility, everything. So now question is that do you have some structure, like for example you have learned some structure in algebra course like group, ring, right? In analysis course also you have learned some kind of structures, right? So here whether do you have some kind of structures on some sets, for example maybe finite sets, infinite sets, right? And topology is one of the tools to understand the structures on this kind of sets, okay? So let me first define what is topology, and then I will give you lots of examples and how to go on those examples. Okay, so formally, so what do you mean by topology? So let me write down. So a topology you start with some set, okay, on a set. The set can be finite, infinite, anything. X, you can say that is a collection tau, say tau, which is a subset of tau, subset of the power set of x, okay? So you know what is the meaning of power set of x. So this is the collection of all subset of x, right? So tau is a collection which is subset of power set of x, and that must satisfy few conditions. So satisfying and the following condition, following properties, whatever you can say, okay? So what is the first property or first condition? That the tau contains that the full set x and the empty set phi. Okay, so this is my symbol for empty set phi. That is what. So mathematically you can write down that x and this phi, they are element of this collection tau, okay? And you know that tau is a subset of the power set, means collection of all subset of it, okay? You can obviously use the fact that, okay, so when I'm using this, actually I mean this can be equal or this can be proper subset also, okay? So tau contains especially these two sets has to be inside tau. One is the full set x, another is the null set, the empty set phi. And property 2, what is that? That say that tau is closed under finite intersection. What does that mean? I will tell you in a minute. Finite intersection of its elements. That is, what does that mean? That means that whenever you choose a finite subcollection of elements, finite number of elements of tau, that is, if you choose something, say u1, u2, some un, is element of tau, then this intersection of ui's are equal to say 1 to n. This is again an element of tau, so this has to be closed under finite intersections. Okay, and the another property is what? Property number 2. Property number 3 tells you that that tau is closed under arbitrary union of its elements. What does that mean? So that is, so if you choose an arbitrary collection, say u alpha, and alpha is some index as the lambda, so it can be finite, infinite. This lambda can be finite, infinite, anything, whatever. If you have this kind of elements, this is, suppose these are this u alpha element of tau, then what happen? Then this union of u alpha belongs to lambda, this union is again an element of tau. So this is the meaning of arbitrary, closed under arbitrary union. So whatever element you choose, and whenever you take the union of these elements which are element of tau, then the resultant union is also element of tau. Okay, so this is the meaning of arbitrary union of closed under arbitrary unions. Okay, so if you have a subset of a power set satisfy this kind of property, then you say that this collection is the topology on the set X. Okay, so and then we say that X and this tau is a topological space. Okay, topological space. Okay, I will come to example. Okay, first let me try to understand properly that obviously this collection may be, there might be many collection on a same set, and generally we say we write down, sometimes we write down only X if you know that what is a topology, or sometimes people also write down X tau to say that this is a topological space. Okay, so these are symbols issued logical space. Okay, so some notations to remember this thing. Okay, so and then obviously you just remark these elements of this tau are called, what they called open sets. Okay, we say that a set is open inside open sets, that is a set is open if uh, it belongs to if it belongs to tau. Okay, so if you choose any set which is subset of x, I mean to say that set means the subset of x. Okay, so x is the kind of universal set here, and if you choose any subset which is open, means that is element of the collection tau. Okay, so yeah, so now I will give many examples one by one. So let us give some kind of general example, then I will come to special example. So examples. Okay, so the obvious one, so if you choose any x and if you choose your collection tau is the power set of x, this is the obvious one, right? Then you want to say that that the full collection power set of x is forms a topology or not, and you can check that obviously number one, you remember x and phi, this is obviously element of the power set of x, right? Because power set contains the null set and also the whole set. And then for finite intersection property, what you need to check? You need to check that whether this satisfy finite intersection property. So you collect any solid. Obviously u1, u2, un. So this is element of power set. So this is subset of x. Then obviously the intersection of ui I equal to 1 to n, this is also a subset of x, and hence an element of subset of x. So that implies that this intersection is an element of this intersection ui I equal to 1 to n, this element of obviously power set of x. Okay, and similarly number 3, if you choose any arbitrary union for any alpha, obviously this is again a subset of x, this is element of power set of x, right? So the power set of x actually forms a topology on any set. Okay, given any non-empty set. If it is empty set, then it's an empty topology, so it's not interesting. So if you start with a non-empty set, then power set forms a topology, and this topology this topology which is tau equal to this power set of x is called the discrete topology. It's very important name, you should remember. Okay, it's called discrete topology on x. Okay, discrete topology on x. So what does that mean? That it can the topology all the open set, all the subset of x are open sets. Okay, so power set is the open set of this. And this is one simple example, trivial we can say. Another such example is it's kind of the opposite of this topology. So what does that mean? That means you start with x and your collection contains only two elements. One is x, another is phi. You know that this has to be inside the element of x. Now if you choose only these two things, this is also element of, this also forms a topology. Now how do you check this forms a topology? So again you need to check that obviously first point is obvious, x and phi, right? Phi and x element of tau, this is obvious. And point number 2, that intersections, right? So you can ask what about the intersections of finite intersection of element of this tau? Obviously if you take intersection of phi and x, it will be phi, and x and x, it will be x, right? So closed under finite intersection okay, and also number 3 points also satisfied, that closed under arbitrary union, right? Okay, so it's obvious that this also forms a topology, and this topology, so this is called the opposite of that, and it has a name. It's called indiscrete topology or the trivial topology, whatever. This is called the indiscrete topology. Okay. Okay, in topology on X. Okay, these are the most trivial one. Okay, that comes naturally, right? But then you can ask, then can you give some kind of example which are giving you some kind of non-trivial topology? There are many such examples. Obviously, one such examples you can have in the on real number, the open sets, right? The forms topology. You can say number 3. So if your X is a real numbers, okay, and your tau is collection of all open sets. I hope you have learned what are the open sets in your analysis course, so I'm not describing here open sets of R. Now you see that this also forms a topology, right? These are called the usual topology or standard topology, or sometimes called equivalent topology. Okay, so many people has many names, so maybe you can either call it is a Euclidean topology, Euclidean topology, or I can say that standard topology. Okay, or you can say that that usual topology, whatever standard topology. So okay, so whatever you said, you should be fine with that. Okay. Okay, so usual topology. Okay, so one more. So this is one example, and then there are many such examples you can define. For example, so let me define it for something for finite sets. Okay, then you will have more understanding. So maybe let me just define my set is something, say 1, 2, and 3. Three numbers are there. Okay, then I want to define a topology on. Okay. Define topology on these sets. So let me check whether this is so maybe I can define tau 1, and this tau 1 is x and phi, and maybe singleton say 1. Okay, now we check whether it forms a topology or not. Okay, so pictorially what you can say that you suppose you have element 1, 2, and 3, and all the elements are inside this ABC, which is X, and null set is obviously null, and also there is a round here. So this means that open sets are only singleton 1 and all 1, 2, 3 and the phi. Now you can check whether it forms a topology or not, and that is also almost obvious, because obviously if, phi and X are element of the tau 1, and if you want to check whether it's close to the finite intersection or not, then it's obvious, because X and 1 intersects with 1, phi with everything is phi, and 1 intersects with 1 is 1, right? So it's close to the finite intersection. And for arbitrary union also, you check that whatever number of union you choose, they will be element of this only, right? Okay, similarly you can define many topologies on this. You can define, say, tau 2 by x and phi and singleton 1. Okay, so once you have singleton 1, then you can talk about you can talk about for example singleton 2 is topology or not. So let's see. So singleton, if you choose singleton 2, I don't know. So let me check whether it's topology or not. And obviously, I mean, this is, you can clearly say that this is not topology, because the union of 1 and 2 is not inside the element of this set, right? So now if we add 1 and 2, there is a topology. Let's see. So what do you see? You are saying that the full thing is open sets. Singleton 1 is open sets. Singleton 2 is open sets. And 1 and 2 is also open sets, right? And now you see that it is a topology. So it satisfies all the conditions, all the three conditions of being a topology, right? Clear? So so there are lots of such examples. Maybe I can give you some more important examples. What was this example? This is 4, right? So maybe 5, and this is very important example. It's called Co-Finite Topology. Okay, so let me write down the name, Co-Finite Topology. Okay, or some people also call finite complement. Oh, doesn't matter. So let me write down the name, Finite Complement Topology. Finite complement topology. Okay, so what is the meaning of that? So it is inside the name, co-finite. So what does that mean? Complement is finite, right? So how to define? So you start with the set X, and then you define your tau, or whatever tau you are defining. What? So it is all the sets subset of X such that either u equal to phi, or u that x minus u. So x, so this minus means set theoretic minus. Okay, so maybe I should write down properly. Yes, set theoretic minus, that x minus u means all the elements which are inside x, not inside u. So this is finite. What does that mean? That means it has finitely many elements. So it can be empty also. Remember, empty set is finite set because empty set has 0 element. Okay, so either the empty set or the complement. So x minus u means u complement. U complement is finite. Okay, so so what does that mean? That means that the open sets are only obviously. Okay, let me check whether it is topology or not, then I will again. So obviously phi is inside tau by definition, because it is in the first condition. Now we want to check x is there or not. Now, so x, for x, what you can write down, x minus x, which is phi, is finite, right? It's a finite set. So obviously x is an element of tau also. So what does that mean? That means phi and x both are element of tau. The first condition is satisfied. Okay, now condition 2. What was the condition number 2? They're closed under finite intersections. So now you check closed under finite intersection or not. What you need to check? So you choose some u1, u2, some un. This is an element of phi. Okay, so what does that is? That is obviously some of them may be phi, so it doesn't matter. So so what does that mean? That means this the ui complement. So let me write down C for complement. These are finite, or obviously ui is equal to empty. But empty thing is trivial, so I am not writing here. Okay, so ui complements are finite. Okay, so now I need to check that so what I need to check? So to check this ui, this intersection I equal to 1 to n is inside tau or not. Okay, that we need to check. Okay, so now to how to check if this intersection is inside tau or not. So I need to check that whether the complement of this set is finite or not, right? So now let us do it. So what does that mean? So x, that complement means x minus intersection of ui's I equal to 1 to n, right? So this is, you can write down now. You remember De Morgan's law. De Morgan's law tells you that this is nothing but, what is the meaning of this? This means that union of x minus ui I equal to 1 to n, right? So this is using De Morgan's law of set theory, right? I hope you guys remember Morgan's law. Okay. So now you recall that these ui complements are finite, right? So these are the ui complements, right? X minus ui are the ui complements. These are all finite, right? Now if you take finite number of elements and take the union, so this is also finite, right? So this is also finite, because the finite union of finite set is finite always, right? Okay. So thus this intersection of ui's I equal to 1 to n, this is the element of that tau. Okay. Is that okay? So this is condition number 2, and condition number 3 tells you that that arbitrary union. So if you choose, so let u alpha belongs to lambda be an arbitrary collection of elements of tau. Okay, so this is arbitrary collection. So we need to prove that this union of this collection is again an element of tau, right? So again, to prove the union, what I need to prove? I need to prove the x minus this union of u alpha belongs to lambda is element of this. But the Morgan's law is true for here also, right? The Morgan's law tells you that this is nothing but intersection of x minus u alpha, right? And alpha belongs to lambda. Now you see that x minus u alpha, these are all finite sets, right? According to the definition of co-finite topology. Now if you have finite sets, and if you take intersection, so that has to be subset of each of those things, right? So intersection has to be finite. So it's also a finite set, right? And hence this arbitrary union of u alpha belongs to lambda, and this is element of the set tau, right? And so we just proved that if you have a co-finite, if you have this collection whose complements are finite, are also forms of topology, and this topology is called for co-finite topology or finite complement topology. Okay, is that clear? Okay, so maybe I can give one more example or some example here. So example number 6 probably. Similarly, you can define something called co-countable. Okay, countable topology. It is inside the name, right? You remember for co-finite topology, what was open sets? Open sets are those whose complement is finite or the empty set. Here the same thing. Here you choose x and you choose tau. Your tau is what? So all the sets inside x, subset of x, is that either x is either u is phi or x minus u, which is u complement, is countable set. So you know the meaning of countable set, I hope, because you have learned in analysis, right? So something is countable means what? So a set is called countable if something happens. If it is finite or countably infinite, right? Countably infinite means you have a map. So either you can say bijective map from the set to the set of natural numbers, that is enough. Or you can say differently. You can say that from the set x, whatever the set, which is countable or not, you need to check it. If it is finite, then it is countable. If it is not finite, then it has to be countably infinite. Then it is called the countable set, right? Now what does that mean? That means you must have one injective map from the set x to set of natural numbers, or a surjective map from the set of natural number to the set x. And this definition you must have learned in your analysis course, so I am not defining again. So this is the meaning of countability. Okay. Now again, you just, this is homework. So you check that if I define by this, then also this forms a topology. So this is homework. This the way I define it, no, countable. So this is actually forms that set tau, or tau, whatever you give the name, doesn't matter. This forms a topology on any set x. Okay, if you choose any set, that will form a topology. Okay, if x is finite, then this is actually the co-finite topology. If x is infinite, then this is no longer the co-finite topology. This becomes a different topology. Okay, so these are the examples. So maybe I will give one more definition, then I will stop today's class. So now how do we compare two topologies? Okay, so here we will define something, and then we will stop our lectures. Okay, so let us start with the set. So let x be a set, and you have two topologies, and say tau 1 and tau 2 be two topologies on x. Okay, we say tau 1 is finer than tau 2, finer than tau 2 if tau 2 is a subset of tau 1. Okay, so kind of as a collection, tau 1 is a bigger collection. Okay, and similarly you can say if it is strict kind of thing, strict subset, then we say that this is tau 1 is strictly finer. Okay, strictly finer, finer than tau 2. Okay, that means it is strictly bigger set. Okay, otherwise which is finer than tau 2. And similarly oppositely, and so in this case we say, okay, so we say tau 2 is coarser than tau 1, coarser or than tau 1, or strictly coarser, whatever, both cases, no, strictly coarser, COARSER. Okay, so what does that mean? So tau 2 is coarser than tau 1 means what? That means tau 2 is a subset of tau 1. Okay, strictly coarser means tau 2 is a proper subset of tau 1. Okay, clear? So this is the meaning of finer and coarser. And what I just started with these sections, that how to compare. So we say that two topologies are comparable. So two topologies tau 1 tau 2 are comparable if either either tau 1 is finer than tau 2, or tau 2 is finer than tau 1. This means tau 2 is finer than tau 1. This means tau 1 is finer than tau 2. Okay. If one of the things happen, then we say these are comparable. Now let us see the example. So you just recall the examples. So maybe okay. So now before that we have some example. Where is our example on finite set? Examples. So here I give two examples, right? Tau 1, which is containing phi this, and another tau 2, this contains that phi x and singleton a1, singleton 2, and singleton 1 2, right? The set 1 2, right? Now the question, this tau 1 tau 2, whether you can compare or not. Okay, so this was the example of what? This was example 4. Okay. Yes. So example, okay, so in example 4, now recall that you have this x equal to 1 2 3 and tau 1 equal to phi, this full set, and singleton 1. Okay, this was the tau 1, and what was tau 2? Tau 2 was phi empty set, and singleton 1, singleton 2, and then 1 2, right? Now here it is clearly that tau 1 is a subset of tau 2, or you can say rather strictly also, whatever. So you can say that tau 1, tau 2 is finer than, or strictly finer, whatever, finer than tau 1. Okay. Similarly, you can say that tau 1 is coarser than tau 2. Okay, this is an example. Okay, yeah, so maybe I will give more example when you learn more things, and this is a very new topic. So let me stop here for today's class, and you can obviously ask your questions on Google Classroom or YouTube. Okay, I will be happy to reply your answer. Okay.